All right, good morning. I'm Scott McMillan. I'm a software engineer at Wargaming Sydney, like Dean said, and today I'm going to discuss cache and memory access considerations in software design. So first, let's have a look at how much time a large game typically spends waiting for memory accesses to complete. To get an indication of this, I profiled several gameplay sessions using Intel's Vtune tool, and the figures I'm going to present are the memory bound metric that it outputs. So this should give us an idea of the average proportion of CPU pipeline slots that are completely stalled waiting for a memory access to complete. So this is a pretty significant proportion of the runtime, as you can see. And the key takeaway here is that if we can make progress improving the efficiency of memory access, it should be able to yield significant performance benefits. All right, so there's nothing special about video games in this respect. Accessing memory is just slow, like hopefully this sophisticated simulation demonstrates. So what does this have to do with the design of our C++ programs? So there's this table getting around latency numbers that every programmer should know, apparently, that you might have seen a variation of. So it shows indicative latencies for common operations such as branch misprediction, hard disk seeking, network transmissions, and so on. You mightn't be thinking of such a table explicitly when you're designing solutions, but taking such values into account is almost certainly something that you do, just to roughly account for the realities of the hardware that you're running on and to marry that with the algorithms that you're deciding to use. It can help to assess the relative merit of different approaches to solving a problem and potentially allow some back-of-the-envelope calculations to be performed before you even write any code. It's pretty hard to avoid being impacted by the CPU's memory subsystem. And we've also just seen that it can be a pretty significant factor for performance. So we've got pretty strong motivation to want to be able to effectively reason about cache usage, compare designs, and assess what's likely to be an efficient solution in the same way. To do that, we need to know more than just access latency figures. What we need to know is a bit more about how the hardware operates. So when it comes to this area, we've got even further motivation to be able to reason about designs and get things right as far as we can, at least initially, because the sorts of changes that are necessary to fix the problems tend to be expensive ones to make. They can be invasive changes to data structures, memory layout, allocators, and so on. If you've got poor design habits in your performance-critical code, you can end up with pervasive issues, and it may reach a point where rectifying the issues is just too costly and your product suffers because of it. So once I've given a little bit of context on the problem space that my team's operating in at Wargaming Sydney studio, I'm going to cover some design guidelines that we found appropriate for having performance-critical systems use cache and memory efficiently, at least in our context. So first I'm going to talk about cache lines. Then I'm going to talk about hardware prefetching. And I'm going to talk about access locality, multiple CPU core considerations, WriteCombineMemory, and address translation. All right, so on my particular team at Wargaming Sydney, we've generally been contributing to the technology of various wargaming titles concerning the graphics layer. So we've also done some work changing game engine architecture, for example, to increase support for multiple cores. We've done some experimentation with virtual reality and porting, and a lot of optimization work related to all of this. So we do this work on PCs, so ranging from DirectX 9 on Windows XP, low specification machines, all the way up to DirectX 12 on modern high-end systems. And we've also done this for games consoles, including PlayStation 4 and Xbox One. So performance in our context means a high and consistent frame rate during gameplay to provide fluid motion. I think Alex explained it really well yesterday when he said it's currency that we can use to buy other things. So we could use it to add extra features to the game. We could use it to maybe support a wider range of users by enabling the game to run on lower system specifications. Or we could just use it to provide a better and more fluid experience for our existing users. So the quote I've shown here was posted onto Reddit after a particular release with some impactful performance optimizations that we contributed to. And I thought it was a pretty good indication of how important performance can be for happy players. If you're making your users feel like crying with happiness, you're probably on a winner. So I've just got a short clip of World of Tanks to give a bit of an idea of the sort of applications that we're dealing with. World of Tanks is a free-to-play, massively multiplayer online game, and this video is showing the rendering in real time using the game's internal graphics engine. All right, so the first topic we're going to talk about is cache lines. So as you can see in this very simplified diagram, transfers from memory and between levels of cache occur in these chunks known as cache lines. For the rest of this talk, we're just going to assume they're 64 bytes, if I don't mention. It can actually be architecture specific, but that's what we're going to do. So we're just going to step through a quick example here. So here we've got this very small cache. It's got 5 cache lines aligned to 64-byte addresses, and now we want to read 4 bytes from memory. So before we can do that, we first need to fetch the whole cache line that 4 bytes exists upon, and then we can access the 4 bytes. So this is pretty good a lot of the time, because say, for example, we want to access the adjacent 4 bytes, as is reasonably common. The cache line's already in cache, and it's fast. So this detail can work less well with some patterns sometimes seen in C++ software. So let's say here we've got this car in our game. Let's say that's at least 64 bytes in size, and we've got this flag indicating whether it's turbo boosting or not. And we've got a collection of these in a vector because we've got a lot of cars in our game. So let's say we want to go through and render some cool flames or something like that and all the cars that are turbo boosting. As we iterate across the vector, as we saw before, we need the Boolean, the cache line that the Boolean exists upon to be fetched into cache, if it wasn't already. So if this has to be fetched from memory, we're basically fetching 512 bits to use 1 bit. So it's a bit of an extreme example, but it demonstrates the issue well. So an alternative design that can work more efficiently in such situations is known as a structure of arrays. So using this approach, we have a single structure representing the group with arrays of data containing 1 element per group member, or perhaps containing groups of members that are frequently accessed together. For the iteration in our previous example, I probably shouldn't have used vector bool at a C++ conference, but just for example, now we should be able to iterate over this, and for each cache line that we fetch, we're going to get data for 512 cars at a time. So let's just look at another example to demonstrate the inefficiencies we can encounter if we don't consider cache line usage. So in this example, we're going to process an 8-bit per pixel grayscale image, and we're going to do just a horizontal pass and a naive vertical pass. So this image data is laid out in memory, row major, so we've got all the pixels for one row, then all the pixels for the next row, and so on. And the only difference in the processing here is that for the horizontal pass, the y-coordinate is the outer loop, and the x-coordinate is the inner loop. And for the vertical pass, we swap those over. So if you just look at this from a computation point of view, it doesn't really look any different, really. But what this implies is that for the horizontal pass, we've got a stride of 1 through the data. So as we're going across the line, we fetch a 64-byte cache line, and it's got 64 pixels worth of data on it. We use all of those, and then we don't use that cache line again. For the vertical pass, as we're going down a column, each pixel that we come to is on a different cache line. So as we go down the column, those have got to be fetched into our cache, and by the time we loop around back to the top, because of the stride through the data here and the dimensions of the image, it's at least going to have been evicted from level 1 and level 2 cache. And what we see is that the vertical pass written like this was 9.0 times slower on my test machine. So just to show exactly what's happening here, I guess you can't really see it so clearly with the contrast here, but we're 0.1% memory bound for the horizontal pass, so basically not limited by memory accesses at all. For the vertical pass, we're significantly memory bound, where 100% of clock cycles are limited by L3 cache access latency. Okay, so let's look at a different class of optimization for cache line usage, just a simple one based on an example from one of Wargaming's games. So The graphics effects can be reconfigured to render different things and to have different appearance. So configuring these was experiencing a memory access bottleneck. So when we were configuring them, the handle that was specified and the new value, and the handle was basically just an index, and that required going and fetching some data from some internal collections each time a new variable was set. And this was occurring at reasonably high frequency. So in order to resolve this problem, all the data necessary to configure new properties was packed down into the handle. So in order to make this efficient, we had to make some compromises on the ranges of supported values so that this could be packed down into 64 bits. And what we've also experienced here is a bit of a denormalization of the data. So this same data still has to exist within the effect system itself. But it seemed like a reasonable approach here, given that this is primarily it's effectively read-only data, to copy it into another layout to make this high-frequency case more efficient. And what we saw here is that this made configuring new resources for graphics effects 10 times faster and configuring new variables for shader programs 3 times faster. All right, so just for this topic, to summarize the key things to remember, transfers occur in cache lines, and you want to get the maximum value from each one that's fetched, basically just so that you have to fetch the minimum number of them. It requires thinking about data structure access in terms of cache lines aligned to 64 bytes. We looked at a few techniques and strategies. I'd really recommend looking at some of Mike Acton's presentations on data-oriented design, if you haven't seen them. And there was also an interesting talk by Chandler Carruth at CPPCon 2016 on hybrid data structures that went through a lot of examples concerning type packing of information. All right, so let's move on to the topic of hardware prefetching. So it's not just about which cache lines you access and the number of them. Predictable access patterns are also very important. So the hardware prefetchers attempt to speculatively load data into cache by predicting what data the program's about to access. And obviously they can only do this if they can predict what data the application is going to need. So this output on the slide was generated by a program I wrote that generates circular linked lists where each node is on a different cache line. So for the red high line there, the linked list had a random ordering, and for the bottom 2 lines, we had a linear contiguous ordering. And you can see the dramatic impact that hardware prefetching has for the predictable access pattern. So prefetchers generally fall into 2 classes, those that prefetch an adjacent cache line and those that look at access patterns expecting a consistent ongoing access stride. So what we want to do is make it so that those can work for us. If we look here at output from the same program as we vary the stride over the data, if you can't read it, the bottom lines are for small strides. The bottom line is for a stride of 1 cache line, so just linear contiguous, and it gets worse and worse as we increase the stride. Yeah, we've still got motivation here to aim for linear and contiguous, and otherwise the smallest strides that we can. And on this particular test CPU, strides over 2 kilobytes, you don't get any prefetch. And when you consider that the data prefetchers generally won't prefetch beyond a page that's already had an explicit load performed upon it, you can sort of see, and considering that pages are generally 4 kilobytes, you can sort of see that large strides can really reduce the benefit that you can get from hardware prefetching. So the key takeaway here is that predictable access patterns can offer large performance benefits. So in software design, attempt to keep access patterns predictable, ideally linear and contiguous. Okay, so let's move on to the topic of access locality of reference. So cache assumes spatial and temporal access locality. So it predicts that if we've accessed data, we're going to access the same data or nearby data again soon. So nearby data is effectively data within the same cache line, like we were talking about before. But accessing data again soon is a bit more complicated to consider. So here's the output for the random access times that I showed before. And the thing to note here is that each time we overflow into a slower level of the memory hierarchy, the penalty to access time is multiple times. So cost differences are this vast, mean that even a small increase in hit rate can have a large impact on overall performance. So that means we can potentially get large performance benefits from reducing the size of the working set, as that means we'll be much more likely to encounter more hits in lower cache levels. So just to get an indicative example showing how much difference this can make, we're going to go back to our simple, naive vertical pass over the image and use something known as loop blocking. So it's not actually the best approach in this case. You can write something that's exactly as fast as the horizontal pass, but for illustrative purposes, this is good. So we are adding extra compute work here. We've got these 2 extra nested levels of loops, and there's some work to maintain filter context between the different blocks so that the processing still works. But what we gain is the ability to adjust the size of the working set of the processing. And if you remember, it was 9 times slower, the vertical pass before. So what we see is that we get a 6.7 times performance boost from reducing the working set size to fit into L1 cache. And you can see how performance degrades as we increase the size of the working set there. So it's not as clear as I hoped it would be, but you can see here, hopefully, that with the large tiles, we're basically as memory bound as we were before. The bottleneck starts to lift as we reduce the tile size. And once we get down to the small tiles, memory access isn't even our primary bottleneck anymore, and we're 0% bound on L3 cache access latency. All right, so let's consider access locality as it applies to some of the collections in the STL. I think it can be pretty surprising how large some of the constant time overheads can become, particularly due to access locality issues. So this is not an exhaustive comparison. That's been done better elsewhere. We're looking to highlight the costs that can be experienced due to issues of access locality. So we're going to use int32 elements, and we're going to be comparing these against standard vector. Larger elements, complex data types, different operations, etc., may shift costs elsewhere and change the comparison. So first we're going to look at standard list. So for each element we add to the list, we've got to do a new allocation. So we can potentially end up with a memory layout as in this diagram. And you've probably seen something like this before. So even if we do happen to get allocations contiguous in memory, there's a lot of size overhead here. So there's at least 16 bytes per element for the previous and the next pointers. So we start to see the impact of the unpredictable access pattern and all of this size overhead when we look at iterating over the elements. And the scan is ON in both cases. So, but the impact of these constant factors means the vector version is 20 times faster. So this alone, without even considering the size overhead and the allocation behavior, it's enough to relegate list to being a niche container, at least for our applications. So vector and arrays. Vectors and arrays tend to be much better defaults in common cases due to the magnitude of these constant time overheads. Your use case may happen to be in the right niche, but make such a decision aware of these costs. So let's have a quick look at the ordered associative containers. So standard map, standard set, they're node-based. They're basically the same as list in terms of the number of allocations and the significant size overhead that they incur. So just as with standard list, this relegates them to niche applications for us. So you'd want to be sure that you're getting quite a lot of benefit from the ordering, insertion behavior, iterator guarantees before you looked at using one of these. So we see here iterating over a set of 32-bit integer elements, similar to standard list, 35 times slower if you can't read that. So profiling with Vtune shows exactly what we expect. It's just completely memory access limited. So just to show an alternative, across a fair range of sizes, it was about 10 times faster to fill a vector and sort it than to build a standard set containing the same elements. And you can also see here that once you've done that, it was significantly faster to search for random integers within that vector than it was to search for them in the standard set. If that's an approach that can work for whatever algorithm you're using, and you don't have particularly large elements or something, this can be highly preferable, or maybe some of the flat map data structures that are available in various libraries. All right, so what about the unordered associative containers? We heard a bit about that before, actually. So they suffer in a lot of the same ways regarding allocation behavior, size overhead, and access locality. So the problem here is that they're required to support reference stability. So pointers to elements are valid even when the hash map is rehashed. So this limits the ability to improve performance and leads to implementations that are effectively an array of pointers to linked lists. And you can see it takes quite a toll on the time required for iteration, just to give an example. So if you can't read that, it was 128 times slower. My workstation at work, when I ran the same test without fast, expensive RAM with big fins on it and stuff, like on my gaming computer at home, it was 176 times slower. If you're just going to do constant time lookups and you ignore the allocation and size overhead limitations, it's not that bad. Maybe if you don't care if things are about twice as slow as they need to be. But improving hash map performance is a huge topic. And one of the common optimizations is to remove this need for reference stability and go to a flat structure. There was a really good talk at C++ Now 2018 called You Can Do Better Than Standard Unordered Map. The presenter has a few implementations available on GitHub, and this yellow line, which hasn't come out so well, that it's showing 9 times faster performance for this operation than the unordered set. So iterating over an unordered set might not be something that you even need to do. But when we look at the lookup performance of the scar flat hash set compared to the standard unordered set, we see that once we get up to the large cases where we can't rely on things being in cache and that sort of thing, the performance is over double. So just to summarize, it's important to be aware of how these collections use memory and the implications for locality of reference, not to mention the allocation behavior and size overheads. If you're thinking about an ideal data layout to solve your problem, it seems pretty likely that it's different to what's on offer here. A good default is to use arrays or standard vector. Many other cases can be covered by a hash table, hopefully one better than what's in the STL. So now a quick mention of allocators. So one reason to use custom allocators is because you want your allocation to be performance. You want your allocations to be faster. So there may be assumptions you can make that the global allocator can't. And yeah, it's pretty frequently the case that you can beat it significantly. But something that's often overlooked is that your allocator can improve performance when you're not allocating by improving access locality. So there was a talk at CPPCon in 2017 by John Lakos on arena allocators that addressed this better than any example I could write, I thought. And all the information is in this paper as well on quantifying memory allocation strategies by John Lakos and others. So one of the tests that they ran to simulate a large system with several subsystems had a large collection of std list of int. And what was observed straight away is that using a local arena for each list provided a significant performance benefit because all of the elements for each list could be allocated contiguously in one block of memory, whereas with the global allocator, it's just good luck, coincidence, if you happen to get things allocated like that. But to simulate a long-running system, their test went through and added and removed elements from all of these lists. And what was observed using the global allocator is significant performance degradation due to diffusion. So all of that fortunate coincidental access locality that might have existed before was lost as all the nodes for all of the lists just got mixed together in memory. And this effect was significantly reduced using local arenas. So just to grab a snippet of their data for these particular parameters on this particular test that I described, the performance benefit was as much as 16 times for using the local arenas. So now I want to show an example of a system that combines some of these things. So just consider a game interacting with a graphics API via an abstraction and management layer. So if you were to structure things like this, the working set would involve all of the high-level logic deciding what to render, the graphics management layer, tracking state changes and trying to make sure that you're using the graphics API efficiently, And it's probably going to involve some of the hardware vendors' code as well. So let's look at an alternative design. So basically, we're going to add this serialization, deserialization step in the middle here. So basically, we're going to serialize the function parameters, basically, that we would have been passing through to the graphics management layer. So a significant amount of effort was put into making sure that these commands are packed tightly so that we can fit as many as possible onto as few cache lines as possible. And we've used a custom allocator here to make sure that the data is written out contiguously in order. And so what we get for the serialization and the deserialization is good access locality and a predictable access pattern. So this is quite flexible. It's we could do the serialization on one thread and the deserialization on another thread. We've got a lot of potential for boosting performance within the graphics management layer because now we're receiving this big batch of work at a time. But without doing any of that, we saw performance improvements of 7% or so on complex scenes just due to the work batching that we've got going on here. So by splitting the working set into two, one that is basically just concerned with the high-level logic and one that's just concerned with submitting to the graphics API, we got that sort of benefit. And profiling confirmed that this performance boost was significantly due to increased cache hit ratios. So the key takeaway here is that locality should be considered both in terms of spatial and temporal locality. So the payoff for accessing data again soon enough to hit a lower cache level can offset the cost of performing some extra computation. The main thing in terms of design is just to consider how the application will be accessing cache lines, including within data containers. Is data going to be accessed repeatedly? What data is accessed around the same time? How large is the working set for an operation? Once you're even considering these things, the various strategies for improving access locality that we've discussed and more are pretty simple to apply, really. All right, so let's move on to the topic of multiple CPU core considerations. So today, you're virtually always designing and analysing software that's running on systems with multiple CPU cores. And if we don't ensure that the interactions between these cores occur efficiently, then we could encounter performance problems. And this primarily relates to how cache is shared and cache coherency mechanisms. So once we've got multiple independent caches, the potential problem arises of having the same value on different caches, different value on different caches corresponding to the same area in memory. So we need some mechanism to deal with this to ensure that we've got data consistency. And the CPUs that we mostly work with do this using a variant of a protocol known as MESI, where cache lines can be in one of these 4 states. So we're just looking at an example of how this works, because I think it gives a pretty good intuition for what is going to be efficient and what isn't. All right, so for this example, we've got 2 CPUs. We're just showing one cache line for each and the corresponding area in memory that starts off with this red value in it. So first, CPU 0 reads that cache line, and it goes into the exclusive state, which means it's only in this one CPU cache, and it matches the value that's in RAM. So next, CPU 1 reads the same value. So the cache line is going to the shared state, which means it's potentially in multiple CPU caches, but it matches what's in RAM. So next, CPU 0 writes to the cache line. So that invalidates the cache line in CPU 1, and CPU 0's cache line goes into the modified state, which means it's only in one CPU cache, and the contents don't match what's in memory. So once we've gotten to this point, CPU 0 could keep writing to this cache line without generating any extra bus traffic, unless there's contention on access to this cache line. And unfortunately, there is. CPU 1 now writes to the same cache line. So the old value from CPU 0 is going to be transmitted to CPU 1 for modification. It's also written into RAM. CPU 0's cache line is invalidated, and CPU 1 goes into this modified state. So next, CPU 0 reads the cache line again, goes into the shared state, receiving the value from CPU 1, and the value also has to be written back to memory because the shared state implies that the value in cache matches what's in memory. So if different CPUs keep writing to the same cache line, a lot of bus traffic is generated by the cache coherency protocol as ownership of the cache line ping-pongs between them. For pure MESI, there's also going to be writes back to RAM at each such transition. So such shared data is something we want to minimize in software for this reason. We don't want to have contention over cache lines for writes or where there's reads and writes occurring. Something that's worth mentioning as an implementation detail is that you can get this sort of situation inadvertently. So for example, if you've declared two variables next to each other and they happen to fall into the same cache line, you can get what's known as false sharing and encounter this sort of problem. And generally you just use alignment and padding to make sure the values go into different cache lines to solve that problem. Okay, so now let's consider work scheduling a little. So for the examples we've got here, the fastest cache levels are private, which means that they're not directly accessible to other CPU cores. Whereas the slower cache levels, they're shared. So they're competitively shared between the local CPU cores in a core cluster, and they're accessible from remote CPU cores. So when a context switch occurs, so a thread switches execution from one CPU core to another, generally the most significant cost is in rewarming of cache contents. So hopefully, and it's often the case that if we switch from one CPU core to a local CPU core that has access to the same shared cache, most of this rewarming is going to occur from accessing cache lines from that shared cache rather than having to refetch them from all the way from memory again. But if you consider the case where, so we've got this remote LLC access latency here for these two example CPUs, and you can see that it's approaching being as bad as reading from memory again, especially for the AMD Jaguar, and this is a best case figure as well. So if you consider a context switch from one CPU core to a remote cluster, this is the sort of cost we're going to be experiencing, not one of those relatively small values for L3 or L2 access latency. So this is something that you really want to avoid. And if you consider the ping-ponging situation that we were talking about on the previous slide, in the context of this remote cache access latency, you can see that there's even more motivation to avoid write contention on cache lines. So even for the read-only case, especially on a fixed system like a games console, you've got motivation to keep related tasks on a single core cluster. So there's limited cache space, and if we've got shared read-only cache lines for tasks with overlapping working sets on multiple CPU clusters, all of those need to have those lines in their cache. And this duplication basically reduces the effective sizes of your caches. If you can schedule more like the right-hand side of the slide than the left-hand side, then you can increase performance because you're effectively increasing the amount of cache space that you've got available. So just as a bit of an example, it's maybe not so clear again here, but there's the bottom blue line that's showing approximately 15% better worst-case frame times than the green line above it. So this was the impact of some minor changes to thread scheduling within an in-development wargaming title. So the primary benefit here was in avoiding those cross-cluster context switches that I mentioned before, and so avoiding incurring this remote LLC access latency. So this is why we saw this relatively large improvement for worst case, which is quite important. If we start dropping frames, it gets noticeable to the player. But the improvement to the average wasn't as large. But we did receive secondary benefit here from keeping two important tasks with non-intersecting working sets on remote core clusters. So Monolith also presented some interesting relevant information from their optimization work on Middle-earth Shadow of War at the Game Developers Conference this year. And for them, some careful management of thread scheduling and efficient data sharing improved their performance by 10%. So the key takeaway here is to consider how data is shared between CPUs and avoid triggering bad behavior. When designing systems, we know that multiple threads writing to different cache lines or reading the same cache lines is okay. What we want to reduce is instances of multiple threads writing to the same cache line or reading and writing the same cache lines. And also be aware of false sharing as an implementation detail. So when it comes to how jobs are scheduled, particularly on fixed systems like games consoles, there can be benefit in using knowledge of how data sharing occurs to improve performance. We want to design our job processing to minimize context switches especially switches to a remote CPU. And ideally, we would have it so that we can structure things to keep shared cache access within a single shared cache. All right, so let's move on to another topic that's relevant for our work programming for GPUs, and that is WriteCombineMemory and associated pitfalls. So keep in mind that a lot of this is x86 specific. So when we write to an area of standard memory, so write back cached memory, the cache line needs to be read into the cache, then it'll be modified, and then at some point in the future it's going to be written back into memory. So often that's good, which is presumably why it's the default. Like you may only want to modify part of the cache line, and maybe you want to read the value you've just written again soon, and so on. But that's not always the case. Consider bulk data writes. So this could be writing large batches of data to transmit to a GPU, or it could be something like output from something like a compressor or something like that, large stream output. So the key property here is that we're writing a lot of data with no intention of reading it again soon. Maybe we're not going to read it ever, from the CPU anyway. It wouldn't be much point generating data that was never going to be read from anyway. In this situation, writing to standard memory, write back cached memory, we get some problems. So that's a waste of read bandwidth, reading in those cache lines to modify them, and we also pollute our cache. So we're potentially displacing other useful cache lines to read these things in. And the problem stems from the fact that there's just no temporal locality here, and so the cache is optimizing for something that doesn't exist. If we write to uncached memory, that solves some of these problems. But we can get small and inefficient writes. And that's particularly bad if we're writing to a device-mapped address range and we start producing a lot of these small writes over the system bus to the GPU or something like that. So WriteCombineMemory, though, it solves a lot of these problems. So for reads, that behaves like uncached memory. But for writes, the writes can be accumulated together in these WriteCombine buffers. So, and once we've accumulated 64 bytes, a cache line, it can be flushed out to memory as nice, efficient bursts. So we'll just take a quick look at how this actually works. So a reasonable guideline due to hardware variations is to assume that there are 4 WriteCombine buffers available per thread, and each can buffer a single cache line. So if we step through an example, we start writing to one cache line, we get allocated to this WriteCombine buffer, and it's now going to accumulate writes for that cache line. Another cache line is going to get accumulated in that buffer, and so on. So you can see we're accumulating writes here. So at this stage, nothing has been written to memory yet. We've just been accumulating writes from store operations in these WriteCombine buffers. So now if we want to write to a 5th cache line, that one gets flushed out to memory as a nice 64-byte burst. And now we're accumulating for another cache line. All right, so hopefully you can see here that this provides a pretty efficient way to write directly into memory, as long as we're okay to relax ordering and we're not going to read the output. But there is a point to this, and there are a few issues that we've got to be aware of here and take into account in our software designs. So if we continue stepping through this example, let's say now we want to write to another cache line. So we had to flush out a partially full WriteCombine buffer there to be able to start accumulating for the next one. We just don't have more buffers available. So writing out a partial cache line like this via the WriteCombiners incurs a significant performance penalty. Think as bad as 5 or 10 times slower if it occurs repeatedly. So we really want to avoid this. So when writing to such a cache line, we need to avoid leaving any part of it unwritten, even if some data isn't changing or it's just padding. We also need to avoid writing into too many streams at once, even if we're eventually going to touch all of the bytes. Because if we switch between streams without doing so, we can again run out of buffers to accumulate in and start incurring this performance penalty. So just to give a bit of an indication here, it's not so clear again, but the top 2 lines here, all the red lines are writing using WriteCombining. The blue lines in the middle there are writing just using standard memory, write back cached memory. So the top 2 red lines, they're writing complete cache lines, and there's no issue here no matter how many output streams that we've got. That red line there that's plummeting down, that's writing 48 bytes to each stream in turn. This particular Intel CPU that I ran on has 10 line fill buffers that get used for this purpose. So that's why performance just flatlines once we're up to 11 streams. But even here, probably 4 is a reasonable number to not exceed. And running on some AMD systems, I've just seen a precipitous drop once you go over 4. And you don't have to be writing to this many streams. This poor performance is what you would see if you're leaving holes in your output when you're using WriteCombineMemory. And one other issue concerning design is that lock prefixed instructions, like you might see if you're using atomic operations and so on, also cause the write combiners to be flushed. So you probably don't want to mix those sorts of operations with high frequency output to WriteCombineMemory. So another issue to be aware of is reads. So obviously when you're designing your system, and it might sound trivial, but in some cases it's not. You've got to design it so that this is one way. You write data and then you never read it again. If you do read, think maybe 100 megabytes a second or something like that. But when this occurs, it's often accidental. It's just things that slip in over time. Maybe you can have innocent looking code, like maybe if you use bit fields, you might be surprised to see reads occurring. Some optimizations can cause reads to occur, but virtually always it's just an accident. It was overlooked, and yeah, I was profiling some code recently and I saw some particle simulation code that was slower than expected, and this was the reason. So what we found is that it can be useful to only expose such memory outside the graphics layer using a write-only interface. So just wrap the pointer up and just don't give anyone the opportunity to make this mistake. So I'll just mention non-temporal rights while we're talking about write combiners because it's related. So these allow writes via the write combiners to standard memory regions that haven't been specifically configured for write combined output. And the intended use case and benefits are similar to what I described earlier. But these also suffer from all the same issues. The issue of partial buffer flushes from using non-temporal rights was significant enough for AMD to discuss it at their talk at the Game Developers Conference this year on optimizing for the Ryzen CPU. Because they've observed this issue in release titles and resolved related issues to improve performance. So yeah, if you're going to use these, you need to be really sure that you're not going to read the memory again soon. It might, often it may sound good, but I think you need a really clear use case, and you've got to, just when you're considering being very sure that you're not going to read the memory again, consider what happens as caches grow over time, as hardware specifications improve. So what wasn't reading from cache before suddenly could be. So yeah, I think before you would consider using these, you've got to have a pretty clear use case. So the key takeaway is that there are several pitfalls to be aware of when using write combiners. So attempt to design systems interacting with such memory to avoid having these flushes of partially written write combined buffers and the consequent plummet in performance. And make sure you design to not need to read from the memory, and the suggestion is to make it so that accidental reads are difficult too. And once again, non-temporal rights have the same pitfalls. If you have a situation where they appear beneficial, you'll have to take all of this into account and more. So let's move on to our final topic, address translation. So briefly, each process generally has its own virtual address space, often made up out of 4 kilobyte pages. So the virtual addresses used by the program need to be converted into physical addresses for the CPU to be able to complete loads or stores. So performing this conversion can be expensive. So the TLB, or translation look-aside buffer, is used to cache recent translations that have been performed. So you can see here the size of the TLB for Intel's Skylake and AMD's Jaguar series, and it doesn't look very impressive, I think. There's only a few dozen entries in the L1 TLB that can address at most a few hundred kilobytes of memory. If translation information isn't cached, you've got to access the page table, which can be a significant cost. So what can we do about this? So from one point of view, you could aim to avoid sparse data structures and try to aim for good access locality at a page level, not just a cache line level. But that's often easier said than done. And we're talking about a really small amount of memory here. So fortunately, there's something else we can do. And pages don't actually have to be 4 kilobytes. Both of these CPUs support at least 2 megabytes. And that's starting to look a lot better in terms of the amount of memory that we can address from cache translations. There may potentially be some assistance for data prefetch, and it means we've got less page table entries in a shallower table. So even if we do have to access the page table, it can be faster. So the performance impact of this can be quite large. So I tried disabling 2 megabyte pages, going back to 4 kilobyte pages for the CPU on a Wargaming console title, and saw that large pages was increasing performance by about 13%. Monolith, to reference their Shadow of War performance postmortem again, reported that they received a 20% boost from transitioning from 4 kilobyte pages on the CPU to 2 megabyte pages. So that sounds pretty good. Why isn't it enabled all the time, everywhere, for everything? So allocating pages, large pages, is very platform specific and doesn't make sense in some cases. So for a fixed games platform, we've got a guaranteed amount of memory, and you never want to consider swapping pages to disk or anything like that. It's a pretty ideal use case. For a game on Windows, for example, it makes a lot less sense. On Windows, special permission is needed to allocate such pages, and when you do, they're pinned into physical memory. They're not pageable. So those two things alone could make for a poor user experience on systems with varying amounts of memory and where resources are being shared with other processes that the user wants to run. And this is assuming we could even successfully allocate that memory. The operating system may take a long time or fail to find so many blocks of contiguous physical memory. So I don't have practical experience with it, but the situation on Linux using a huge TLB page sounds fairly similar. There is transparent huge page support, but it sounds like there are some considerations there in using that too. So the key takeaway here is that address translation can be a significant cost. Consider using large pages for maximum performance if it makes sense for your application. For example, if you're running on a dedicated machine with no desire for paging to disk, it seems like a pretty clear win. From a software design point of view, if you're using a platform where large pages isn't transparent, the implications are primarily for a memory allocation. So it's likely that you're going to need your own allocator. You might just need to use your own heap allocator. All right, so I think it's pretty apparent how much performance can be gained from efficient cache and memory access, and then we need a bit of insight into how CPU caches work to be able to do this. In the end, there's just a few core guidelines. So design taking into account cache line size granularity for accesses, design for predictable access patterns with high spatial and temporal locality, designed to minimize cache coherency overhead and scheduling costs in multi-core systems, aware of performance pitfalls when using write combining, if that applies to your application area, and potentially design systems to use large pages, once again, if it's appropriate for your particular applications. None of this reduces the importance of measurement and profiling. Measurement, I would say, is the most important thing if you're working on a performance-critical system. But hopefully you'll end up in a better spot initially and have more understanding of future changes that are required. All right, thanks for listening. If anyone's got any questions, I think I must have spoken relatively fast because I've got 10 minutes.
Hi, good talk. Regarding your testing of strided access, have you tried any of the prefetch intrinsics, especially when your strider isn't, predictable? Or if you've got like a sparse data structure and your strider is kind of going all over the place?
So in that particular test, I didn't try using software prefetch. I know AMD, in their same talk at the Game Developers Conference, was recommending against using hardware prefetch and recommending to instead try to trigger the hardware prefetcher. And they gave some examples where inserting software prefetch instructions disabled certain compiler optimizations and those sorts of things. But yeah, in general, software prefetch, I don't think we're using it anywhere in our applications. And so it hasn't often been of assistance to me. Generally, when I've tried using it, and I have, the overhead was higher than the benefit I was getting, and generally things were just able to be structured so that it wasn't necessary. But yeah, they can be useful in some cases, obviously.
Yeah, thanks. It was a very good talk.
Thank you.
You emphasized the importance of measurement, and I guess part of that is trying to analyze the results of measurement. So you use Vtune for the other things, obviously. Do you have any other tools that you use to profile, like cache performance or anything? I know like Insomnia Games released some like a cache simulator.
Yeah, their tool was quite interesting.
It's amazing.
We haven't used it, so that basically triggered an exception after every instruction. So it was very slow, but yeah, Vtune is the main tool that I use, and I don't know of any other tools that people are using within the studio for that purpose other than Vtune. Vtune is free now, if people didn't know. You've got to register again every 3 months for your free commercial license, but yeah, I just have it. I've got it on this laptop. I've got it on all my computers and use it all the time now. It's nice.
I'm curious. Did you measure the team's performance to make changes before and after the optimizations?
Sorry, the team's performance, did you say?
Yeah, like the team's ability to change the same code that you changed for optimizations.
So are you wondering whether the code became more complicated?
Yeah.
Yeah, well, I guess it's always a trade-off, and when you're presenting a talk just focusing on performance optimization, it might seem like this is the only thing that you're focusing on and all of your code is going to be complicated. But yeah, it's just common sense and trade-offs. Like we saw in the talk yesterday, like some code, it's better to just be easy to read and maintainable, and other times it's worth the cost of complexity if you're actually getting something for it. So in some of the examples I listed here, it was just better. It wasn't actually more complicated. So we don't have metrics to see how efficient changes were before and after, but any of the examples I gave, actually the command-based stuff that I was talking about for the graphics API, we actually got rid of a lot of issues, and it was, I think anyway, quite a lot nicer afterwards. Basically, the only issue there was due to the deferred processing. So if a crash, say, is encountered processing the commands, then if you don't have any sort of support there to tell you where that command came from, you could be like, well, this is a bit harder to track than it was when I just had a call stack going all the way down. But in debug builds, we just store the call stack with each command that's generated, so it's actually pretty easy. So yeah. Hopefully that's a reasonable enough answer for your question.
Yeah, thanks for a very, very information-rich talk. I was just curious with the loop blocking you talked about, whether you'd looked at any, I guess, strategies for sort of automatic loop blocking in terms of algorithms like a piano curve or Hilbert curve for walking kind of multi-dimensional data structures in a way that, yeah, provides more efficient access.
So in terms of parameter tuning, are you talking about to optimize the loop blocking sizes and things like that?
I guess I'm specifically referring to, yeah, the Hilbert curve and the piano curve and whether or not they are effective or efficient ways for walking any sort of size data structure.
Yeah. I did have a slide that I deleted, and it looks like I probably could have kept it in. I had slides on data-oriented design, and I had one that specifically, because this is something that we see in graphics programming. So if I'm getting what you're saying correctly, so Morton order is something we more often see, so like a Z order pattern walking through data and those sorts of things. Those sorts of things are definitely something to think about in software design. Like how can you so even storing the image data in tiles rather than as row major, like the example I was using. When your video card fetches texture data, it's sort of a location-based problem. Sort of like sometimes some applications dealing with, map data and those sorts of things. When you access a particular pixel, it's very likely you're going to want to access nearby pixels, particularly for bilinear filtering. So having things in tiles can make it so you're less likely to access multiple cache lines, but also using a Z order pattern, Morton order, can make the access pattern through memory more performant too. So hopefully that answers your question to some extent.
Yeah, I have a lot of questions. So you guys ship your titles across multiple platforms, I guess different architectures, different cache sizes. How do you design your data structures to be efficient across all platforms? Is it like finding a common factor or specialization for Xbox or PS4?
A lot of this stuff is just better for all platforms, I would say. Like even if you've got different cache line sizes. So if you optimize to access less 64-byte cache lines, even if you've got 128-byte cache lines, it's going to be better for the most part. A lot of the stuff with work scheduling is different between PC with a lot of hugely varying specifications and console, where you know that you've got a very particular set of hardware specifications that you can optimize for. So for us, I think generally the biggest difference comes in there where you're on consoles, you can optimize for a very specific hardware configuration. But in general, a lot of this stuff, concerning hardware prefetch, cache line sizes, just optimizing for better locality of reference, it benefits all platforms, I would say.
I have a question. So you were showing how to design your code so that it would be friendly to these things. Have you looked at or considered the impact of what your compilers and your optimizations would do to the code you wrote?
So I guess if I understand the question correctly, that the compiler generally doesn't offer much assistance in these sorts of cases. So the compiler can't change your data structure. It can't make standard unordered map better or anything like that. Generally, so like I mentioned with write combining, there are a few implementation details to look at there where the compiler can do bad things. But in general, we haven't seen differences on different compilers. So we use several different compilers, and we haven't really seen differences concerning a lot of this.
So the follow-on question is, if for the loop tiling, right?
Yeah.
Have you seen compilers do funny things and auto-vectorize your stuff for you?
You sometimes see auto-vectorization. I haven't ever really seen compilers do much of value related to that. One funny thing I remember once was using Intel's compilers. It got very happy in the output saying it had multi-threaded something, and it was just like a vector clear or something like that. And I think that's about it. I haven't really seen anything very advanced and very useful happen related to most of this.
Yeah, a lot of questions. So we talked about profiling the CPU side, but what kind of tools do you use to profile like your shaders or your graphics API usage on like Windows, for example?
So that sort of varies within the team. I use NVIDIA Insight. A lot of people use RenderDoc, but NVIDIA Insight has been updated significantly recently. If you've seen it, used to be integrated into Visual Studio, and now it's a separate application, and they've made a lot of progress on exposing a lot of the underlying, say, shader residency and various hardware counters and that sort of thing to make it so that you can know exactly what your application is doing. And AMD have similar tools as well, but I like NVIDIA Insight. So.
Regarding like standard library data structures, have you tried things like EASTL or PLF colony or PLF list? which are kind of more kind of cache-aware containers?
So not at work. I've tried EASTL at home and that sort of thing. I've looked at Abseil. I think there's a link I had on the slide. It might be a bit hard to go back to it. But this, it's a much more comprehensive comparison than what I've done, and not just focused on highlighting access latency issues. And so I haven't tried PLF Colony, and one of the reasons was that I looked at these performance benchmarks and thought, why would I want to use that? But so this particular link, and if you search in your search engine, there's another set where he does do some testing with Colony. Abseil has some. They just added their flat hash map implementation recently, and there's a fixed vector. So we're not using those, but I think there's some promise in some of those. And the implementations that from the speaker at that C++ Now talk, I did try several different flat hash sets, and his ones were very fast and very good, I thought. So very interesting talk, and the code looks at least very fast anyway. So thanks.
That was all we had time for. Thank you very much, Scott.